A very warm welcome once again, everyone, to the Maritime Education Podcast. My name is Barry Sadler, and today I'm going to be discussing fires, in particular fires on board car ships. Although it hasn't made the news in any particularly great way, there have been two significant fires on board car ships that have broken out during February 2025. One of them was on the Grande Brazil in the English Channel, which led, of course, as many of you may have seen from the news, to the evacuation of all 28 crew members on board. The other one happened just a few days later, February the 21st, on the Grande Congo, which suffered a fire while sailing in the Atlantic near Bermuda. Now, on this occasion, the crew successfully contained the fire and the ship proceeded without further incident to Newport News in Virginia Beach. These two incidents, very, very close to one another, have started to re-energise the argument regarding the carriage of vehicles at sea, and in particular, the carriage of electric vehicles at sea. Is it a coincidence that we are seeing an increased amount of fires on board car ships, or is this closely related to the fact that electric vehicles are becoming more popular and their transportation becoming more prolific? As we transport these cars and we witness some of the events that can happen when there are faults within the cars themselves, we fail to mention sometimes trends and patterns that indicate we are heading towards a significant event. The transportation of electric vehicles is subject to debate, massive debate. Do we transport the electric vehicles fully charged? Do we transport them partially charged? Do we transport them completely discharged? What is the safest and most appropriate way to move electric cars from one place to the other? Fires on car ships, and on particular on roll-on roll-off ships, have been common in the past. If you think about it, it's an incredibly hazardous cargo and hazardous operation to engage in. You're taking multiple vehicles full of different types of fuel. Some of those vehicles carry different types of cargo within the trailers at the back. You're parking them all in a very, very confined space on a ship. You're then taking them to sea and you're chucking them around a bit. If you think of it like that, it almost seems madness to carry more than just a few vehicles at a time on a ship that puts to sea, particularly on a ship that puts deep sea and starts to encounter bigger waves, heavier seas and more challenging conditions that really do test the parking abilities of the stevedores and the lashing abilities of the crew. But nonetheless, world demand for electric vehicles and cars in general necessitates ships that are built to carry not just hundreds but thousands of vehicles in one go. Companies like Tesla insist on chartering entire vessels to move their electric cars. So instead of just having a couple of thousand of cars amongst perhaps 8,000 being electric, when the ship has been chartered by a company that produces electric cars, the ship's going to be full of electric cars. So 4,000 to 6,000 of them can be transported at any one time on a car ship. So with these new challenges being thrown at us, it's really important to understand why we have started to see failures on some of these cars, and in particular failures that lead to problems within the fuel cells of these cars. Electric vehicles use lithium-ion batteries. Lithium-ion batteries are widely used due to their high energy density and the rechargeability of the batteries. They carry enough energy when put together in very, very large cells to power cars and their systems over many, many miles through many, many hours. Your average electric car will perhaps give you between 200 to 250 miles of range. So this means that the batteries have got to be big enough to provide the power in order to move the car along at speed, and also to provide the power to ensure that the car's systems, simple systems such as heating, lighting, wipers, demisters and things like this, continue to operate even with the drawdown on the power for the electric motors themselves. So when we consider the amount of energy that a lithium-ion battery is able to hold, it's not surprising that if this energy is not used in a way that it is designed to be used, then there can pose a risk of both fire and electric problems. The most critical risk of any lithium-ion battery is something called thermal runaway. Basically, what thermal runaway is a self-sustaining chain reaction that occurs when a lithium-ion battery overheats, and this leads in turn to further temperature increases and ultimately causes failure within the battery itself. The sheer nature of a lithium-ion battery means that most of the reactions within the battery that produce the energy that's used to power whatever the battery sits in is contained within a self-sealed unit. In other words, you've got the lithium electrolytes themselves, but these are contained within a sealed box. The trouble with thermal runaway is that with all of this stored energy within the battery, once thermal runaway starts to happen, then it's difficult for the energy that's produced within the thermal heating itself to escape. This can cause not just damage to the battery, but if the heat starts to escape from the battery, in other words, if the box that the actual components are contained in fails, then that heat starts to escape. When the heat starts to escape, this causes exothermic reactions, which means that we get a release of heat along with a release of gas from inside the sealed unit. If the pressure inside the unit has increased due to the buildup of gas, this can cause the batteries, of course, to explode, and that in itself is incredibly high risk. The trouble with thermal runaway is that it will generally start within a single unit, and then the cascade effect from this single unit means that the heat that's coming out of the single cell spreads to neighbouring cells, and this accelerates the failure of the entire battery system, which can result in fires, explosions, the generation of toxic gases, and a rapid rise in temperature. Thermal runaways can in fact reach over 1000 degrees Celsius, and therefore they are very much capable of starting to ignite materials around them, not just create cascade effects in other lithium-ion battery cells that are nearby. Now, there are lots of different reasons why lithium-ion batteries fail. They can be overcharged. This is something that the circuitry of a lithium-ion battery will hopefully prevent, but sometimes if they are overcharged, this can cause short circuits. Over discharging is also a problem. So we mentioned earlier on that some carriers were debating whether or not to transport their cars with the batteries fully discharged. This can be a problem in itself. Some of the batteries may have physical damage, or poor manufacturing may have created defects which can increase the possibility of there being thermal runaway. External heat exposure is another reason that thermal runaway can start, and this is sometimes the case on car ships where your electric vehicles are stored for prolonged periods of time on car decks where the heat may be fairly extreme. A car ship travelling from a relatively cool climate through a relatively warm climate can experience very, very large increases of temperature within the holds themselves. and unless those holes are ventilated properly, they can reach very high heats, which to you and I would perhaps just feel like a very hot place where it's not particularly pleasant to work. But to a lithium ion battery sitting there exposed to that heat on a continuous basis, it may create a failure of the lithium ion battery itself. Lithium ion batteries can also emit toxic gases. Hydrogen fluoride, carbon monoxide and organic solvents can be expelled from a lithium ion battery that is failing. It can also emit hydrogen, and we'll talk about that a little bit later on. So back to our thermal runaway. Thermal runaway is the number one risk with a lithium ion battery, and it can be caused by lots of different things. We've talked about a lot of them: overheating, overcharging, internal short circuits may happen, external damage and over discharging. But these all relate to the start of the process rather than the actual process of thermal runaway itself. Over discharging is an interesting one. If you over discharge a lithium ion battery, then what happens is copper in the anode dissolves and redeposits on the cells, and this creates potential short circuits which can cause thermal runaway. I say this is interesting because if you try to transport a car that has been totally discharged on the battery, and somehow something in the car drains the battery even further, so it could be something as simple as the alarm trying to go off, or some sort of function of the car which is still connected to the battery can continue to drain it. When the battery becomes over discharged, it can create a short circuit. This short circuit will use the remaining energy within the battery to cause thermal runaway. The initial trigger of thermal runaway is, of course, the heat generation. The causes that we have mentioned before will cause the battery to start to heat up. So basically, membranes within the battery will start to weaken, and this will start to allow the heat to break down the internal components. Once the battery has reached between 80 and 120 degrees Celsius, what we go into is a decomposition of the electrolytes within the battery itself, and this starts to generate heat. The lithium then reacts with the electrolyte, and this forms hydrogen gas, which we'll come back to a little bit later on. Once we start to get up to 200 degrees Celsius, the process starts to accelerate even further as the separator melts, causing internal short circuits within the battery itself. These internal short circuits start to further decompose the electrolytes, and this starts to release large amounts of hydrogen, carbon monoxide and methane to a certain extent. Thermal runaway happens once that temperature starts to flick above 200. There's no turning back. The cathodes start to decompose, which releases oxygen. The oxygen fuels, if you like, the thermal runaway even further, so that eventually the electrolytes within the battery vaporize and ignites. The battery then enters basically an unstoppable self-heating reaction. Above 500 degrees Celsius, the battery will either explode if the casing to the battery hasn't failed, as we discussed, or it will start to burn violently. Flames can then spread to adjacent cells and adjacent batteries, causing a domino effect within battery packs, and the thermal runaway starts to make its way through the entire fuel cell setup. Obviously, preventing thermal runaway is really crucial, and battery management systems do a lot of this. They provide thermal protection to the actual batteries themselves. They prevent overcharging and over discharging. They monitor temperature and voltage and can shut things down if things start to get hot. Fire suppression systems are available for these batteries, such as aerosol extinguishers, inert gas systems which can be pumped into the battery compartments, and ventilation systems to displace flammable gases. But at the end of the day, thermal runaway is something that every seafarer needs to be on the lookout for. Early detection of thermal runaway is, of course, very, very important. This means regular rounds of the car decks, ensuring that fire detection systems are working well. Thermal imaging sensors are often put on car decks that carry large amounts of electric vehicles, and these are able to see thermal images of the thermal runaway at a very, very early stage. Emergency cooling or liquid cooling systems can be installed into cars so that if thermal runaway is detected, then liquid cooling systems can be used to cool down the battery. Don't forget, if we can keep the battery below 200 degrees Celsius, we will severely reduce the risk of thermal runaway, the process that's unstoppable. Once the temperature goes above 200 and the cells start to break down at that increased and accelerated way, that's when thermal runaway is almost unsurpassable, and we cannot, unsuppressible I should say, and we cannot stop what's going to happen, and that is the eventual total meltdown of the battery itself. Class D extinguishers, which are lithium specific extinguishers, can be used. These rely heavily on a cooling effect. They are an aerosol type extinguisher, which basically uses a very, very slick foam that evaporates incredibly quickly. A little bit like an aerosol, rapid evaporation causes rapid cooling, and so these lithium fire extinguishers, Class D fire extinguishers as they are known, rely heavily on the cooling process. Now, if the battery's thermal runaway is arrested by being significantly cooled, that's great, but temporary cooling will only suspend the thermal runaway. And so one of the big disadvantages with a lithium specific fire extinguisher is that it's almost a one-shot event. If you're using the extinguisher to suppress the heating and cool the battery again, if you can stop it, great. But if there's energy still left within the battery and the cause of the thermal runaway is still present, then eventually the energy will reheat to the point at which you will need to use another fire extinguisher to cool it down again. Obviously, you've only got a certain amount of fire extinguishing material available on board, so constantly having to do this will deplete supplies very, very quickly. You must never use water on large battery fires. It seems obvious, but if you use pure water, this can cause further thermal decomposition by causing even more shorts throughout the cells, and that may accelerate it. Water will of course cool, but the cooling effect will be basically overcome by the amount of short circuit that will be created by large amounts of water. Removing unaffected cells to prevent chain reactions is another good way to prevent thermal runaway from its domino effect, but accessing a car to be able to do this by seafarers that are firefighting, very, very unlikely for that to be able to happen. Thermal runaway is a serious safety hazard, and maritime applications of firefighting extinguishers, storage, transportation of batteries at the various charging levels, this is all still under a lot of investigation and all still under a lot of research in order to come up with the safest means to transport these large battery packs. Until we have really good definitive advice on the carriage and firefighting of electric vehicles, it's incumbent upon every seafarer involved in the transportation of these cars to be aware of the potential hazards that are associated with huge banks of lithium-ion batteries, and to monitor the cargo on a regular basis. I said we'd talk about hydrogen, and the reason I want to talk about hydrogen is because I was discussing with an expert the fire on board the Fremantle Highway some months ago, which was proven to be the result of a lithium-ion battery fire. One of the things that he told me is that the deck above the fire had raised up quite a bit because there was an explosion that happened when the fire started. And the explosion that happened was because the batteries in question released huge amounts of hydrogen. And this is something that I think it needs to be, seafarers need to be aware of in order to deal with the problems of lithium-ion batteries. During thermal runaway, lots of gases are released, but one of the most dangerous gases that can be released is hydrogen. Hydrogen is, of course, an explosive gas. When it combines with oxygen and a source of ignition, then you can have an explosion if it's contained, particularly within a car deck. Hydrogen itself is generated by the thermal runaway process. It gives off all sorts of gases, as I have previously stated, but one of those gases being hydrogen. Now, hydrogen is 14 times lighter than air. So the trouble with hydrogen is that as it's given off from the batteries during thermal runaway, it will rise above and fill the space above the cars. In other words, when you're looking at a car deck where you've had a thermal runaway on it, the hydrogen will be sat at the deck head. Now, this is well out of the way until a source of ignition reaches that hydrogen that's sat by the deck head, and when that happens, the hydrogen ignites rapidly. This causes an explosion, and therefore sometimes the seafarer's response to a fire, i.e. shut down everything and try to let the fire burn itself out, may not be the best form of approach when dealing with thermal runaway. So if thermal runaway has happened, then hydrogen has been produced. That hydrogen, if the battery has failed, will have escaped from the battery and will be gathering at the deck head. Therefore, if you've got thermal runaway that is in process and it's obvious that the fuel cells have degraded and have failed, in other words, the signs of not just smoke but perhaps flame or spark escaping from the battery packs, then it's worth doing controlled ventilation, allowing the air at the top of the car deck to escape, taking with it the potentially explosive hydrogen, may avoid a catastrophic explosion further down the line when thermal runaway causes the battery to explode, which emits burning material, and that burning material is more than capable of igniting the hydrogen above it. So don't be afraid to try and controlled ventilate the space when you've got thermal runaway carrying on. It's a seafarer's nature, as I said, to immediately lock down the hold, but it may be worth considering not doing so to allow these hydrogen emissions to escape. Hydrogen has a very, very wide flammability range. That's one of the reasons why it explodes so readily. Between 4 and 75% in air makes it highly explosive in an enclosed space. And therefore, if your lithium-ion battery is emitting hydrogen in a poorly ventilated space, it will very, very quickly form an explosive mixture with air. And that's why, once again, we should consider ventilating the space that our thermal runaway is happening within. Hydrogen is obviously ignited by any kind of source of ignition. The exploding battery can ignite hydrogen, static discharges can ignite hydrogen, or a worsening lithium-ion battery fire. The temperatures that are created by that fire can actually ignite the hydrogen through a temperature rise in its own without there actually being a spark, static discharge, flame or other ignition source. So The build-up of hydrogen and the lack of a spark doesn't mean you're not going to have an explosion, because the heat generated by the thermal runaway can be enough to ignite the hydrogen purely through a high temperature. It's really important that seafarers and owners who are moving large amounts of electric vehicles continue to push the research into the safest way to carry electric cars and deal with electric car fires. I am aware that certain manufacturers are putting a lot of money into the research of these incidents, and in particular the research into having to deal with these incidents at sea. But for the time being, those involved with firefighting on an electric vehicle need to be aware of the necessity to cool the area down as quick as possible, to ventilate the area to remove the hydrogen, and to have plenty of firefighting material available in order to constantly keep the temperature of the battery low, so that the thermal runaway process never has chance to run away before the energy in the battery is properly dispersed. I hope this podcast has given you a little bit of an insight into some of the dangers associated with lithium-ion batteries and the carriage of cars at sea. I'm pretty sure that we're going to see an increasing amount of incidents going forward until we get some definitive way of fighting the fire which we can implement on a fleet-wide basis to ensure that seafarers have the best chance possible to control, extinguish and prevent thermal runaway if it happens. Fires on car ships are at a high. Let's hope that we've reached a peak and that further research can start to bring these numbers of events down. Having 2 major car fires 3 days apart in the last month is becoming unacceptable. Thanks a lot for listening, everyone. We look forward to speaking to you again on the next podcast. Have a great day.